Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good day to all. Okay, welcome back class. How are you? Today I will share with you about the parametric design. This topic about the design phase in flow, information flow, parametric design of bolt is an example, parametric design of belt and pulley, some systematic parametric design, and summary. Okay, from the configuration design, okay, here we have for the configuration for a special purpose, we have some features, arrangement, relation dimension, attribution list, standard part, and type attribution list. Okay, then from there, okay, we finalize the parametric design variable value, what the size, what the dimension, material to process. So we study about the performance, prediction, overall certification, and prototype test result before we go to the detailed design. Okay, this example of work. Okay, we have a parametric design for the length, for total length, and we have a total thread here, and D for the shank, and we have a left and right for tensile force. This is an example. Okay, now we to mode of failure under navigation is tensile yielding. Okay, example. Okay, we know about the F equal to AS, meaning area and strength. Then after the example here, we have we estimate the strength must greater than 4,000 pound. Okay, here, and then we substitute the formula, F more than 4,000 and AS more than 4,000 pound. 4,000 pound about the 2 kilo. 2,000, yes, is 1 kilo, around about the 2.2 pound. Okay, after we arrange, okay, A go more than 4 over the S, then we get the, for area we get the 0.047 inch square. Then we substitute the area, okay, with the formula pi diameter 2 over the 4, and then we get the final is about the nominal size about the 0.25 inch. For the proof strength versus diameter graph, okay, this curve graph, okay, from the here about the 2.4, okay, 2.4 something here about here, and then requirement is 4,000 here. Okay, from here we can estimate the green, the blue color is flexible, and then the inflexible in the yellow color. Okay, meaning when you design, you need the diameter more than 2.47 to get to 4,000 pound. Okay, this is a step how we can solve the problem. First, review the concept and the configuration detail, read the situation detail. Okay, estimate, examine a sketch of the part. Okay, we can sketch by 2D side view, identify the mode of failure to example here tensile, determine the variable proof of load was constraint, obtain analytical relationship for FP and the area, and then we substitute the juggle the question to find the D. Okay, this is a systematic parametric design. Okay, from here, from after we get the diameter and proof of load more than 4,000, okay, the select variable, design variable D equal to 0.1 inch. Okay, here the flow is from the formatted problem with generative and analyze, and then we do the redesign. Okay, this is a standard flow for schematic parametric design. Okay, here we have a 2D design. The idea for the another example for the belt design problem. About the pulley, motor pulley and grinding wheel pulley. Okay, this is a driver, this is a driver. Okay, you know this top one and radius 1. Okay, radius 2 and top 2. The distance is C. Okay, study using the free body diagram where we get the force 1 and force 2 here. Okay, this formatting the parameter. Okay, this detail about the solution the parametric study. Okay, we have a belt torque, the belt tension is the force, center distance. Okay, this C unit here, and we know the lower limit. We set at Tm, upper limit now. Okay, potential belt tension we set 35, and the distance we the small one. Okay, from here we certified the w.r.t belt tension. From here we get the certification is about the 30 pound. Okay, more than 30 pound is we get to near to 0. Okay, 35 is 0, meaning we design under 30 pound. So from the center distance, okay, certification is 1 is 5, from 0 to 5. Okay, more than 5 until 20 we set is less than more than 0 for certification. Design variable is thing of form. Okay, this from center distance we set the lower limit. Okay, not set for upper limit. Driven pulley distance not set. Okay, then we set the problem definition parameter. We know the friction coefficient F. Okay, belt strength F max, motor power this W that dot, motor pulley diameter is D1 inch. Okay, this all the set the lower limit was 0.3 for friction coefficient. The maximum also 0.3. This is not change. Belt strength is 30 pound of the upper limit is maximum. Okay, motor power is half. Okay, of power, and then motor pulley diameter set at 2 inch. After we get okay this example parametric value can be the non-numeric and discrete. Okay, example. Okay, type of numerical length is the value inch or cm. Non-numerical is about the material process configuration is like the aluminium machine. Okay, the trade continuous is height. Okay, we can be in the inch or meter. Discrete is the tire size, lumbar size is you can list the standard. Okay, discrete binary example zinc coating, safety switch example with off without. This is standard. This we have 2 item for discrete. Okay, this additional information for you all, what they call numeric, non-numeric, okay, continuous and discrete. Okay, we call back. Okay, from the how to get the from the science subject. Okay, we have physics also, chemistry or material. We call from engineering, we have a statistic, dynamic, fluid. Okay, this study thermo, okay, transfer, kinetic, all this for the you can recall from the engineering. And then we do conduct the experiment. Also from the physics principle you can apply all the physics principle to get your parametric design. Okay, here we have a conservation energy, okay. Any energy cannot destroy of the crate. Okay, conservation of mass, conservation of momentum, and so on lah. Okay, another, okay, you can use all the basic principle, the formula you learned before. Okay, from here this Newton, okay, Newton symbol, okay, and this for static and so on. So you can recall this for this formula. Okay, you also can use using the spreadsheet. Okay, from the parameter, we have symbol, unit, and value. Okay, and also we have for design variable. Okay, it's for input and also output. Okay, for output in characteristic, okay, we can be motor torque, grinding wheel speed, angle of arc, belt tension out, belt tension slack, okay, initial belt tension, and so on. So we have some constraint here. Okay, this minimum we set, either this 300, okay, certified, below than 35 is uncertified. Okay, and then more than 35 is certified. Okay, the example use this target value. Okay, after that we can set this target value from distance, how much distance, how many inches, okay, the center. Okay, how we set the distance, we get the belt tension. Okay, okay, also we have using the Q, overall certification. Okay, weighting rating, as we used as before. Okay, we use this method. Okay, we have tension and compactness. Then we use the table for study our value. Okay, parameter. Here we have a parameter about the 4.96. Okay, the force we get the 35, and the S to F1 is 0, W F1 is 0. Okay, and we can do using the formula before. Okay, after that, how we can get it? Can get the maximum Qmax. Okay, Qmax. Here we maximum for this value is the center distance is 10. Okay, this maximum value is 0.72. Okay, here we get the for the center distance. Others, we can also using the function specification result from the form. Okay, from customer specification, product function. Okay, form plus a given, and SAP. Example here, acceleration of the motorcycle, customer specification, how fast, okay, how many fast, how many kilometer hours, and also the additional acceleration is a force, power, weight, and transition, okay, plus a fuel consumption and so on. This during the customer certification. Okay, here we can also add the certification for the distance. For the distance there. Okay, you have parameter for belt tension. Okay, the blue color. The pink color for compactness. This linear curve, linear line. Okay, overall certification is about the green color. Okay, okay, then we get the more this area lah. The yellow area is possible for certification. Okay, back to this systematic parametric design. Okay, the same concept idea, you can do the selection variable, select the value for design variable and predict performance, check the feasible function and manufacturer, and select the best alternative. Okay, this is a method what you can do. Okay, and then this mean calculate experiment and using the Qmax to set the final decision. Okay, next we have a design for roundness. Okay, method to reduce the sensitivity of product performance to variance such as, okay, modern manufacturing is material and process, wear, and also regarding the operating environment. Current method you can use the Taguchi method. Also you can use a probabilistic optimal design. Both methods are statistic and probability. Okay, this for today's summary. The parametric design phase involves the decision making process to determine the value of the design variable that must satisfy the constraint and maximize the customer satisfaction. The 5 steps in the parametric design are formulated, okay, generate, analyze, evaluate, and refine or optimize. During the parametric design analysis, we predict the performance of each alternative. Reiterating means redesign when necessary to ensure that all candidates are feasible. During parametric design evaluation, we select the best alternative. Example, assessing the satisfaction. Many design problems exhibit trade-off behavior, necessitating compromise among the design variable value. Weighted rating method using customer satisfaction curve, a function can be used to determine the best candidate from among the feasible design candidate. Okay, thank you class for your attention. See you next time.